All right, section 13.2 is all about independent and dependent events. Our objectives are to determine whether events are independent, find probabilities of independent and dependent events, and find the conditional probabilities. And then our essential question, how can you determine whether two events are independent or dependent? All right, let's talk about determining whether events are independent. So independent events means that the occurrence of one event does not affect the occurrence of the other event. So this is one of our core concepts. In words, two events, A and B, are independent events if and only if the probability that both events occur is the product, super important, product, of the probabilities of the events. So our symbols are probability P of A and B, so events A and B multiplied together. All right, so example 1, determining whether events are independent. A student taking a quiz randomly guesses the answers to 4 true-false questions. Use a sample space to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. So we can use the same sample space in example 2 that's located on your interactive notebook pages 138 or in your textbook page 707. So we actually looked at an example similar to this in 13.1. So let's say the correct on question 1 probability is 8 out of 16, which simplifies to 1/2. The probability that we're correct on question 2 is also 8 out of 16, which equals 1/2. And then correct on question 1 and question 2 would be 4 out of 16, which simplifies to 1/4. Since 1/2 times 1/2 is equal to 1/4, the events are independent. All right, let's look at example 2, also determining whether events are independent. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So we know that we have 3 girls, so let's make a chart over here, or look at our chart. If the number of girls was 1, our possible outcomes is girl 1 and boy, or choosing the boy and then girl 1. And then for the next, we would have girl number 2 and then choose boy, or we could choose the boy first and then the girl number 2 next. So you can see how the pattern goes. You would look at all the possible outcomes. So if we chose the girl first, that would be 9 out of 12. So let's count our girls here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible instances where the outcome is the girl first and then the boy out of a total of 12, which simplifies to 3/4. Now let's consider the girl second. So our possible outcomes for girl second would be 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12, which simplifies to 3/4. How about the girl first and then the girl second? So that would be 1, 2, 3, 4, 5, 6 out of possible 12, simplifying to 1/2. So to determine whether these are independent, we want to see that 3/4, so 3/4 times 3/4, see if it equals 1/2. And it does not. So these are not independent events. All right, let's find probability of events. So dependent events is the occurrence of one event which does not affect the occurrence of the other event. So this is another core concept, probability of dependent events. If two events A and B are dependent events, then the probability that both events occur is the product of the probabilities of the first event and the conditional probability of the second event, given the first event. Keywords here, new keywords, conditional probability of the second event given the first event. And notice the new notation, a little bar in between event B and event A. And we are multiplying. So we want the product of probability of event A times the conditional probability of the second event given the first event is how you read this notation here. All right, so looking at our example 2, given the one that we just finished, the girl first and then the girl second. So if we multiply the probability that the girl's first, which is 9/12, times the probability that the girl's second, given that the girl is first, which is 6 out of 9, simplifies to 1/2. So our dependent event probability is 1/2. All right, example 3, let's find the probability of an independent event. As part of the board, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. So let's define event A as 5 on the first spin and event B as greater than 3 on the second spin. So the probability of event A is 1 out of 8. And that's as simple as it gets. Probability of event B occurring is 5 out of 8. And that's from figuring out how many numbers are greater than 3. So the numbers greater than 3 are the 4, the 5, the 6, the 7, the 8. So that's 5 out of total 8. So you get the product of the two events, 1/8 times 5/8, which comes out to be 5/64. Convert to decimal, decimal 0.78, convert to percent, 7.8%. So the probability that you get a 5 on your first spin and a number greater than 3 on your second spin is about 7.8%. Now let's find probability of dependent events. We have a bag that contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, then you randomly draw another bill from the bag. Find the probability that both events, A and B, will occur. So we'll define event A as the first bill is $100. We'll define event B as the second bill, $100. So the probability of event A is 5 because there are 5 desirable $100 bills out of total 25 bills. There are 21 $1 bills plus the 5 $100 bills for a total of 25. Probability that the second bill is 100 is 4 out of 24. Notice we subtracted 1 off the 5 to be 4 and 1 off the 25 to be 24. That's because we're dealing with dependent events because we set the bill aside once we draw it out, which means we're not putting the bill that we drew on the first event back into the bag. So there's one less bill that we could potentially draw out of the bag. So you subtract 1 off both numerator and denominator. Now multiply the two events together, getting 5 25ths times 4 24ths, which simplifies to 1/5 times 1/6, which is 1/30th, which is approximately decimal 0.33, which is 3.3%. So the probability that you draw two $100 bills is about 1/30th, approximately decimal 0.33, which is approximately 3.33%. All right, so now let's compare independent and dependent events. You randomly select 3 cards from a standard deck of 52 cards. What's the probability that all 3 cards are hearts when, option A, you replace each card before selecting the next card, or B, you do not replace each card before selecting the next card? Compare the probabilities. So we'll start with you replace each card before you select the next card. If this happens, then that means you're looking at independent events. So the probability that A and B and C occur, we would multiply the probability of event A times the probability of event B times the probability of event C. There's 3 cards. The 13 out of 52 times 13 out of 52 times 13 out of 52. And you're multiplying those 3 fractions because there are 3 cards randomly chosen out of a full deck of 52. So the probability that you pull 3 cards that are all hearts, well, there are 13 of each suit in a deck. So that means there are 13 possible hearts in a deck of cards. And I'm putting the card back, so that means I still have a total of 52 in the deck each time I draw a new card. So when I multiply all this together, it simplifies to 1/64, which simplifies to square root of sorry, not the square root, decimal 0.16, which is approximately 1.6%. All right, for the second event, it's going to be dependent because I'm putting the cards back after I draw. So the probability of event A times the probability of B given A times the probability of C given A and B. So the first draw would be 13 out of 52. There's a full deck, and there are 13 possible hearts to choose. I don't put the card back, so that means I subtract 1 off the 13 and 1 off the 52, making it 12 out of 51. Times, again, I do not put the card back, so I'm multiplying 1 less on the numerator, so that's 11, 1 less in the denominator, which is 50. Multiply all that together, you get 11 out of 850, which simplifies to decimal 0.13, which is approximately 1.3%. So when you compare by dividing, so 1/64 divided by 11 over 850 is approximately 1.2 times more likely to select 3 hearts when you replace each before you select the next card. Now let's focus on conditional probabilities. We'll use a table to find conditional probabilities. Quality control inspector checks for defective parts. The table shows the results of the inspector's work. Find A, the probability that a defective part passes, and B, the probability that a non-defective part fails. So we'll start with part A. The desire is that our part passes, so that's in the numerator, out of the total defective parts. So that's going to be 3 out of 3 plus 36, because defective total, pass or fail, is added together to be the total in the denominator. So do all your different forms, so it simplifies down to 1/13, which is decimal 0.77, or about 7.7%. Part B, our desire is to figure out the number of non-defective parts that fail, and that's going to be 11, as we can see on the chart, out of the total number of non-defective parts, which is 450 plus 11. So you also want to include the ones that pass. So that simplifies to 11 over 461, which is approximately decimal 0.24, which is 2.4%. All right, so hopefully you can kind of figure out that there's maybe a little formula that you can use to figure out the probability of dependent events. So you can write like this rule. So this is a little rule that you can write in your notes and refer to it, highlight it, in order to set up your rule for finding conditional probabilities. Remember, it's the probability of event A times the probability of event B given A occurs, which is the same as saying probability of A and B. And that would become probability of B given A equals probability of A and B divided by the probability of event A. All right, so finding conditional probability, knowing this new formula, let's try it out. At a school, 60% of students buy a school lunch. Only 10% of the students buy lunch and dessert. What's the probability that a student who buys lunch also buys dessert? So event A, we will define as buys lunch. Event B, we will define as buys dessert. So we know that the probability that A occurs is decimal 6, 60% converted to decimal. And then we know that the probability of event A and B occurring is 10%, decimal 1. All right, so next you would set up your formula. So the probability that event B occurs given A would be the probability of A and B divided by probability of A. So divide 0.1 by 0.6, which simplifies to 1/6, which is approximately decimal 167. So the probability a student buys lunch, also buying dessert, is about 1/6. All right, just a little fun fact here, and that's all for today. See you in class.